Synthesis, characterization, and electrical studies of ZrV2O7/polyaniline nanocomposite. Abstract conducting polymers containing inorganic metal oxide materials integrates the material's properties and applications. Chemical oxidation polymerization method was adopted to prepare polyaniline/zirconium vanadate, ZrV2O7/PANI, nanocomposite. In situ polymerization reaction was performed for successful synthesis of PANI/ZrV2O7 nanocomposite. Structural characterization and morphology of the composite was carried out by X-ray diffraction, XRD, and scanning electron micrograph tools respectively. Particle size and bonding nature of the composite was studied by transmission electron micrograph, TEM, and Fourier transform infrared, FTIR, tools. Variation of the electrical behavior of the composite sample was also studied. Keywords: chemical oxidation, nanocomposite, ZrV2O7, XRD, SEM, TEM, FTIR. Introduction: conducting polymers are attracted by recent researchers because of its good electrical conductivity, which finds many applications 1 to 2. Polyaniline, PANI, is one of the noted conducting polymers and it can be synthesized by the oxidative polymerization of aniline monomer in the presence oxidizing agents 3 to 4. Different oxidizing agents, like ammonium persulfate, APS, hydrogen peroxide etc. have been used in the synthetic procedures 5 to 6. The formation of PANI composites with inorganic materials provides new synergistic properties that cannot be attained from individual materials 5 to 7. Thermal stability, mechanical strength 29, fire retardant properties and processability can be enhanced by the composite materials 810. When materials like metal oxide nanoparticles combined with PANI matrix, resulting nanocomposites integrates the material's properties and applications. Recent research shows PANI composites has been successfully synthesizing with varied nanomaterials like metal oxides for its commercial applications 11 to 12. The present work reports the chemical oxidation polymerization method for the preparation of PANI ZrV2O7 nanocomposite. As prepared composite was well characterized by various characterization tools. Electrical properties like DC and AC studies of the composite were studied for its electrical behavior. 2. Experimental. 2.2 Preparation of ZrV2O7 PANI nanocomposites. Zirconium vanadate nanomaterials are prepared as per the literature method Rev. ZrV2O7 nanocomposite is prepared as follows. 0.1 mole of aniline was dissolved in 1 mHCl to form aniline hydrochloride. Zirconium vanadate is added in the 50 weight percentage of aniline hydrochloride solution with vigorous stirring in order to keep the zirconium vanadate suspended in the solution. To this reaction mixture, 0.1 m of ammonium persulfate, NH4, 2S2O8 which acts as the oxidant was added slowly with continuous stirring for 4-6 hours at 050 C. The precipitate powder recovered were vacuum filtered and washed with water and acetone. Finally the resultant precipitate was dried in an oven for 24 hours to achieve a constant weight. Lastly all the synthesized composite so obtained above is crushed into fine powder in an agate mortar in the presence of acetone medium. The synthetic scheme is given in figure 1. Preparation of pellets. The powders of polyaniline ZrV2O7 nanocomposite so obtained is crushed and ground finely in the presence of acetone medium and agate mortar. This powder is pressed to form pellets of 10 mm diameter and thickness which varies from 1 to 2 mm by applying pressure of 90 MPa in a hydraulic press. 2.3 Characterization transmission electron microscopy, TEM, was carried out with Hitachi 7100 and Techni G2 transmission electron microscopes operating respectively at an acceleration voltage of 75 kV and 200 kV. Scanning electron microscopy, SEM, images were obtained with a Leo 1530 microscope operating at an acceleration voltage of 5.0 kV. Fourier transform infrared, FTIR, spectra were recorded on a per-clinometer spectrometer. X-ray diffraction measurement was performed with a Philips Pro Expert Plus diffractometer. 3 Results and discussion. 3.1 XRD analysis. X-ray diffraction pattern of polyaniline ZrV2O7 composite with 50 Wt% of ZrV2O7 in polyaniline is shown in figure 2. It is seen that the peaks of zirconium vanadate indicates the crystalline nature of the composite. Most of the Bragg S reflections observed in the pattern are due to the presence of dispersed zirconium vanadate nanoparticles. The obtained despacing values are matches well with standard JCPDS file JCPDS No 01-088-0587. The peaks obtained for composite materials are also on the same 2. Values of the zirconium vanadate. 3.2 FTIR analysis. The polymerization of aniline to its polyaniline with zirconium vanadate nanocomposite was well confirmed by infrared study. Figure 3 shows FTIR of its prepared PANI ZrV2O7 nanocomposite sample. The bends at 1563 and 1481 cm1 are attributed to C equals N and C equals C stretching mode of vibration for the quinonoid and benzenoid units of PANI. The peaks at 1300 and 1236 cm1 are assigned to C and stretching mode of benzenoid ring. The peak at 1239 cm1 is the characteristic of the conducting prorogated form of PANI. The bends in the region 1011-10 cm1 are due to in-plane bending vibration of CH mode. The bend at 820 cm1 originates out of plane CH bending vibration. Peaks below 1000 cm1 are attributed due to the presence of metal oxide complexation in PANI. 3.3 Scanning electron microscopy, SEM, analysis. Figure 4 shows the SEM image of the as prepared PANI ZrV2O7 nanocomposite. It is observed from the SEM images that the distribution of metal oxide particles are agglomerated due to the formation of matrix mixing or close complexation. Most of the particles are in spherical shape and are complexed with polymer forms by matriomixing, which enhances the crystalline nature of the PANI. 3.4 Transmission electron microscopy, TEM, analysis. Figure 5 shows the typical bright filed TEM image of the synthesized PANI ZrV2O7 nanocomposite. It can be seen from the image that the oxide particle are well dispersed and forms polydispersed polymer matrix. Varied particle sizes are observed and most of them are spherical and hexagonal in shape and are in the nano range. 4 Electrical conductivity study. 4.1 DC conductivity analysis. Figure 6 shows the variation of DC conductivity as a function of temperature of as prepared PANI ZrV2O7 nanocomposite. The conductivity increases with increase in temperature. The DC conductivity of composite exhibits an exponential behavior in a temperature range 800 C to 1400 C. Initially the conductivity values are almost constant up to 80 C and then increases slowly due to behavior of disorder in semiconductor. The analysis of temperature-dependent conductivity data suggests that the charge transport mechanism in PANI can be explained by the variable range hopping, VRH, model. 4.2 AC conductivity analysis. Figure 7 shows the variation of AC conductivity as a function of frequency of PANI ZrV2O7 nanocomposite. The conductivity increases with increase in frequency is observed in the figure. The AC conductivity of composite shows almost constant conductivity in the frequency range 102 Hz to 104 Hz. After this, the conductivity increase with increase in the frequency, especially in the 105-106 Hz range. Lattice polarization around a charge in localized state may be responsible for multiple phases of conductivity in the composite. 5 Conclusions. Chemical oxidation polymerization method was used for the successful preparation of metal oxide/polyaniline nanocomposite. The enhanced crystalline nature of the composite is observed due to insertion of inorganic metal oxide materials. Both DC and AC conductivities carried over the composite shows the presence of polarons as charge carriers and confirm the extended chain length of polyaniline.